You just finished taking both parts of your test, first test in calculus, and so now you're going to take a moment and grade your exam. So I'm going to go through your solutions or the solutions to this test, and you'll see that on the top here it will tell you right next to each problem how many points that problem is worth, and if there's multiple parts of that problem, how many points each part of that problem is worth. If you've shown your work, you got your problem totally correct, the answer right, you didn't have any mathematical statements written in there wrong, and then give yourself full credit. If for some reason you have some little small error in there, maybe you multiplied wrong, forgot a negative, then knock off a half a point to a point depending on how many points that problem is worth. And so this first problem is looking at limits, and you're looking at the following limits, and you want to state if it does not exist, you want to explain why. And so for limits, first thing that you want to do is you want to look at direct substitution. And so for this first one, we have this limit as x goes to 3 pi fourths of 2 cosine of x. And so this is equal to, we're just going to go in and we're going to plug in 3 pi fourths wherever we see an x, and so we have 2 cosine of 3 pi fourths. 3 pi fourths, that gets us into the second quadrant. Our reference angle is pi fourth. Cosine in the second quadrant is negative, and so this is equal to 2 times cosine of 3 pi fourths is negative root 2 over 2. Oops. I already put my negative out there, don't need it twice. There, that's wrong. So then 2's cancel, and so this is equal to negative root 2. So for the next one, part B, you're going to go in and you're going to plug in 0 wherever you see an x in this function. And so if you do that though, you're going to get 6 times 0 raised to the 5th power minus 8 times 0 cubed. That's 0 in the numerator all over 9 times 0 cubed minus 6 times 0 to the 5th, which is also 0. If you get something in the form of 0 over 0, that's indeterminate form, so this means that you need to go back and manipulate this a little bit more so that the limit will tell us something. And so one of the things that you might want to try is to factor. And so let's look at this and let's pull out what we have in common in the numerator. So let's pull out an x cubed, and we can actually pull out a 2, but I realize doing solutions that let's just pull out the x cubed, it will make our life easier later. So pulling just out the x cubed, this leaves me with 6x squared minus 8 all over. And so here in the denominator, I'm just going to pull out the variable that they share in common. They both have an x cubed in common. And so if I pull out the x cubed, this leaves us with 9 minus 6x squared. We can cancel like factors. We have an x cubed in the numerator, x cubed in the denominator, so those cancel. And so now when we go in and do our direct substitution and plug in 0 wherever we see an x, we're going to be left with just a negative 8 in the numerator all over a 9 in the denominator. And so our solution is negative 8/9. So for part C, go in, do direct substitution. If we do this, though, in the numerator we get a negative 1/4 plus a 1/4, which is 0. All over, plugging in 0 where we see an x in the denominator also gives us 0. Indeterminate form, so then we want to go back in here and we want to manipulate this. And so one way to help is if you have a complex fraction, try to rewrite this so that it's no longer a complex fraction. And so we can do that by multiplying by a fancy one. And that fancy one that I'm going to do is, we're going to look at the denominators of the fractions within our main fraction. So I have an x minus 4 in one fraction and a 4 in the other. That common denominator is x minus 4 times 4. And so we want to multiply that fancy one. We want to use that LCD. So 4 times x minus 4. And multiply that to the numerator. Multiply that to the denominator. And so when we distribute this to each term in our numerator, we're left with the limit as x is going to 0. Well, x minus 4s are going to cancel, just leaving us with a 4. Plus, and when we distribute it to the next piece in the numerator, the 4s cancel, just leaving us with this x minus 4. All over our denominator of x, all times 4 times x minus 4. Let's simplify by combining terms in our numerator. And so I have a 4 minus a 4 cancels. We have an x just left in the numerator, all over x times 4 times x minus 4. I notice my x's cancel, the one in the numerator denominator. And so now when we look at the limit as x is approaching 0, of 1 over 4 times x minus 4, plugging in 0 wherever we see an x, we get 1 all over 4 times negative 4, which is equal to negative 1 over 16. So part D, we're looking at a limit again. This limit here, where we would plug in 5 wherever we see an x. If we do that though, we get 5 minus 5 in the numerator, which is 0, all over plugging in 5 wherever we see an x in that denominator. We have the square root of 5 plus 4, which is a square root of 9, which is 3. 3 minus 3 is 0. So again, we have an indeterminate form, and we need to manipulate this so we can find the limit. This has a radical in it, so you want to try multiplying again by a fancy 1, but this time we're going to multiply by the conjugate, in this case of the denominator. So the conjugate of this denominator is the square root of x plus 4. Change the sign, so plus 3. So looking at this, we have the limit as x is approaching 5. Let's not distribute the numerator. Only the piece that we want to distribute is what we were multiplying the conjugate by. When we multiply the conjugates, these binomials, these are difference of squares. So if I square my first term, this is just x plus 4. Minus squaring my second term is 9. So we have x minus 5 in the numerator, all times square root of x plus 4. Outside of the radical is a plus 3. All over, simplifying that numerator, we have x minus 5. So we have factors that are similar or the same. X minus 5s cancel. And so we're left with a limit as x is approaching 5 of the square root of x plus 4 plus 3. So we want to go in here wherever we see an x, we're replacing it with 5. And so we have here square root of 5 plus 4, which is the square root of 9, plus 3, which is equal to 3 plus 3, which is equal to 6. So part E, we're looking at the limit as x is approaching 0 of sine squared of 2x all over x squared. So we want to use the fact that sine of x over x as a limit as x goes to 0 is 1. And so we can manipulate this so that we can get that to fall out. And so let's rewrite this. This is the same thing. The sine squared of 2x is the same thing as sine of 2x times sine of 2x. So rewriting this, we have the limit as x is approaching 0 of sine of 2x times sine of 2x all over x squared. But x squared could also be rewritten as x times x. And so this is almost in the form that this is equal to 1. We actually need to manipulate it so our denominator has a 2x. So sine of 2x over 2x, the limit as x goes to 0 is 1. And so we can do that by multiplying by a fancy 1. And so I need 2 2's down in the denominator. I can write it as 4, or 2 times 2. And multiply the numerator by 4. And so now, and we can bring our coefficient out front by rules of limits. So this is the same thing as 4 times the limit as x is approaching 0 of sine of 2x all over 2x times sine of 2x all over 2x. So taking a limit of a product is the same thing as a limit of each factor. And so this is going to 1 and 1 times the 4 in front. So this is equal to 4. So part D, we're looking at the limit as x is approaching infinity of negative e raised to the negative 2x minus 5. And so let's go in here and let's plug in infinity wherever we see an x. Actually, before we do that, let's manipulate our limit a little bit and rewrite e to the negative 2x to have a positive exponent by bringing it down into the denominator. And so doing that, we have the limit as x is approaching infinity of negative, this is like negative 1 all over e to the 2x, using rules of exponents, minus 5. And so now when we go in there and we plug in infinity wherever we see an x, well, 1 over e to 2 times infinity, 1 over something that is growing and getting huge, that piece is going to 0. So this piece is going to 0 as x comes to infinity, minus 5. Well, 0 minus 5 is negative 5. Okay, so that was number 1. Number 2, we have a piecewise function, and we want to find the limit as x is approaching 1. And if it doesn't exist, we need to explain why. In order for a limit to exist, the left-hand side has to equal the right-hand side. So when we look at the limit here, as x is approaching 1 on the left, well, that's for values which are less than 1, and so we want to use the first equation. So x over 2 plus 9/2. So we're going to go in here, and wherever we see an x, we're going to plug in 1, and we get back 1/2 plus 9/2, which is 10/2, which is equal to 5. So now we want to look at the limit as x is approaching 1 on the right-hand side. Well, those are values for x is greater than or equal to, well, greater than 1. And so we're going to use the equation then x squared minus 6x plus 10 on that piecewise function. And so going in here and plugging in 1 wherever we see an x in this function, we get back, this is 1 squared minus 6 times 1 plus 10. And so this is equal to 1 minus 6 plus 10. 1 minus 6 is negative 5. Negative 5 plus 10 is 5. Since our limit on the left is the same as the limit on the right, the limit as x approaches 1 of f of x is equal to 5. So that problem was worth 5 points. Problem 3, we're looking at the limit as x approaches 6 of this function. Well, when x is not 6, we use this function, the first equation, x squared minus 5x minus 6 all over x minus 6. And so that's the same equation that we would be using on the left and the right. If I plugged in a number close to left, 5.99999, that would be telling me to use equation 1. If I plug in 6.01, that would be telling me to use equation 1. So when I look at the limit as x is approaching 6 here, of x squared minus 5x minus 6 all over x minus 6, and we go in here and we plug in a 6 wherever we see an x, well, we have 6 squared minus 5 times 6 minus 6 all over 6 minus 6. So let me reduce. I notice I have 0 in the denominator. And in my numerator, 6 squared is 36 minus 5 times 6, which is negative 30, minus 6, so that we get 0 in over 0. So it looks like I need to factor, and I notice if I factor my numerator x squared minus 5x minus 6, that factors as x minus 6 times x plus 1 all over x minus 6. We're going to simplify by canceling like terms or factors, and now we're going to go in and we're going to plug in 6 wherever we see an x. And so when we do that, we have 6 plus 1, which gives us 7. So right now we found that the limit as x is approaching 6 of our function f of x is equal to 7. Now part B tells us that we want to find the value of k such that the limit as x approaches 6 of f of x equals f of 6. Okay, well, we just found what the limit as x approaches 6 of f of x is. We found that that was 7. And if we go up here, we want to look at what f of 6 is. So if we look at f of 6, we look at f of 6. So we plug in 6 wherever we see an x in that equation. Well, when x is 6, we're using the second equation, 3k plus 2. Well, notice that there's no value there of x. So when we plug in 6 wherever we see an x, well, there's no x. We have 3k plus 2. And we want this to equal our limit. So we want f of 6 to equal our limit, which we found to be 7. So we want to find k such that 3k plus 2 is equal to 7. Well, let's find k. So isolate k, subtract 2 on both sides. We get 3k equals 5. Divide both sides by 3. We get k is 5/3. So we found the value of k such that the limit as x approaches 6 of f of x is equal to f of 6 when k is 5/3. Okay, so number 4, let g of x be the given function. G of x is equal to f of x plus a if x is less than or equal to 0. Or it's equal to 3 minus b times cosine of x if x is greater than 0, where a and b are constants, and f of x is equal to 1 minus x squared. show that g of x is continuous at x equals 0 if a equals 1 and b equals 1. Okay, so again, g of x is equal to f of x plus a. We're going to go in here. We are given what f of x is. F of x is this 1 minus x squared. And we're going to go back in and we're also going to plug in 1 for a. So let's rewrite g of x with this information. So g of x is equal to f of x, which we just saw was 1 minus x squared, plus a, which is 1, if x is less than or equal to 0. Now let's look at the second equation. We have 3 minus b, but b we're going to choose to be 1. So 1 times cosine of x if x is greater than 0. So we can simplify a little further. G of x is equal to, first equation, 2 minus x squared if x is less than or equal to 0. And it's 3 minus cosine of x if x is greater than 0. So we want to show that this is continuous now at x equals 0. And x equals 0 is the only place that we might have a problem because we know the function 2 minus x squared, which is a polynomial, is always continuous, and 3 minus cosine of x is always continuous. And so the only problem we would have is when they change equations. And so let's look at the limit. And if we can show that the limit on the left is the same as the limit on the right, we know the limit exists. So that has to hold true for it to be continuous. F of that number that we're taking the limit at, so in 0 in this case, has to exist. It does because it's part of our domain. And it has to be the same as our limit. So looking at the limit as x approaches 0 on the left, that would be values less than 0, and so this would be using the first equation, 2 minus x squared. Plugging in 0 wherever we see an x, we get back 2. Now let's look at the limit as x is approaching 0 on the right. And so this is the equation for x greater than 0 on the right, so that would be the second equation, 3 minus cosine of x. If we plug in 0 wherever we see an x, this is equal to 3 minus cosine of 0 is 1. So this is also equal to 2. Since these are the same, the limit as x approaches 0, g of x is equal to 2. So now let's look at f of 0. If f of 0 is 2, then we know and showed that it's continuous at x equals 0. So looking at g of 0, so we want to look at which equation we need to use. Well, when x is 0, that tells me to use this first equation. If I go in here and I plug in a 0 wherever I see an x, I have 2 minus 0 squared, which is 2. So the conditions hold that it's continuous at x equals 0. And then the last problem on this portion of the exam, we want to use the following table to answer. And so they give us that the function f and g are continuous. They say that the function h is given above the table. And we want to explain why there must be some value t that is in the interval between 1 and 2 such that h of t would be negative 2. Okay, so if f of x is continuous and g of x are continuous, then f of g of x also must be continuous as long as f is defined at g of x, at some value x there. And then x minus x is also continuous, so the difference of those two continuous functions also must be continuous. And so let's look at the n values. Let's plug that in wherever we see an x here. So let's look at what h of 1 is. So h of 1 is equal to f of g of 1 minus 1. Let's change that color. Well, it's already given us some information, or we have the table here. So f of, let's look at what g of 1 is. So when x is 1, g of 1 is 3. So we have f of 3 minus 1. Well, f of 3, let's go over here. When x is 3, f of 3 is negative 3. So we have negative 3 minus 1. So we found that h of 1 is equal to negative 4. Now let's look at the other n value of our interval, h of 4. So plugging it into this equation here, we have this is equal to f of g of 4 minus x, which is 4. So this is equal to f of, well, g of 4, let's go over here. When x is 4, g of 4 is 2. So f of 2 minus 4, let's look at f of 2. F of 2, when x is 2, f of 2, y is 8. So this is equal to 8 minus 4, which is 4. So we found that h of 4 is 4. Okay, by the intermediate value theorem, we know that there has to be some value of x between 1 and 4, some value t between 1 and 4, such that the y value of h, our h value, is going to be negative 2. So technically, we found that h of 1, so if I was to graph this function, when x was 1, h of 1 was negative 4. And at 4, h of 4 was positive 4. And we want to know, say that there is, or prove that there's some value at negative 2, or some value between 1 and 4 that's going to give us a value, y value of negative 2. And by that intermediate value theorem, because we have a continuous function, I don't know what's going on in between here right now, but it has to cross. That y value equals negative 2. Okay, so that is the first exam, or first part of the first exam.